Our goal in this section is going to be to look at linear transformations from a vector space V to a vector space W. And these vector spaces will be finite dimensional. So let's say V is n dimensional and W is m dimensional. And you've got a linear transformation between them. Let's call that linear transformation T. Well, if V is n dimensional, then V, from a linear algebra point of view, is identical to Rn. There's no way to tell them apart. And W, from a linear algebra point of view, is identical to Rm. Again, there's no way to tell them apart. Well, if you had a linear transformation from V to W, and you did not have a linear transformation from Rn to Rm, that would be a way of telling them apart. So this linear transformation T must have some corresponding linear transformation T hat from Rn to Rm. And we'd like to study this function T hat. So let's attach some bases to V and W. V is n-dimensional, and it has a basis B. W is m-dimensional, and it has a basis C. Then there are multiple isomorphisms, but we'll look at the particular isomorphism that takes a vector and maps it to its coordinate vector. How is this T hat going to work? So we've got a vector x in V that's being mapped to T of x in W, and x is identical to its coordinate vector from a linear algebra point of view, and T of x is identical to its coordinate vector from a linear algebra point of view. So we're going to define T hat of x in the natural way. T hat of this coordinate vector equals this coordinate vector. T hat had better be linear because if this is a linear transformation and this isn't, that gives us a way of distinguishing these points from these points that only uses linear algebra. And such a method of distinguishing points shouldn't exist because these spaces are isomorphic. They're identical. In particular, if T hat is a linear mapping from Rn to Rm, there must be a matrix such that T hat is equivalent to matrix multiplication. In the next set of notes, we'll look for this matrix.